All right. So in the last part of the lecture, we looked at kind of a brute force method to solve for the effects of finite gain in an operational amplifier. And in this part, we're going to look at a little bit more elegant technique using basic feedback analysis. So with our op amp that we were looking at in the last part of the lecture, just a basic non-inverting op amp, we had something that looked like this. And we can treat this like a negative feedback system, just a single loop, first order negative feedback system. Where we have a summation feeding into our gain stage that has some finite gain, A of S. And then we have a general block, beta, that represents the feedback in the system. We take our output from the output of the amplifier and put our input into the input of the summer. And we have a voltage, VA. And in fact, let's, instead of calling this VA, call this V beta, our feedback voltage. All right. In general, when we have this type of system, we can write an expression for V out in terms of V error. So first of all, we can say that V error is equal to VI minus V beta. And we know that V out is equal to VE times A of S. If we substitute for VE, we get V out is equal to VI minus V beta times A of S. And solving for V out over VI with respect to S, we can show that this gain is equal to A of S divided by 1 plus A of S times beta. Okay, so what is beta? Well, beta is the amount of feedback we get from the output to our inverting terminal. So we can find beta by using the beta circuit, which is simply RF and R. So it's a voltage divider. So we can say that beta, or V beta, is equal to R1 divided by R1 plus R2 times V out. We can define beta as being V beta divided by V out, which is equal to R1 divided by R1 plus R2. All right, so now let's substitute everything in for A. And remember, A of S is equal to A sub 0 divided by 1 plus S divided by omega H. It's a one-pole roll-off with a finite DC gain. And if we substitute this into our gain formula, we get V out over VI with respect to S is equal to A naught divided by 1 plus S over omega H divided by 1 plus beta times A naught divided by 1 plus S over omega H. Simplifying this, we find A naught divided by 1 plus beta times A naught times 1 over 1 plus S divided by omega H times 1 plus beta times A sub 0, or A naught. This is a DC gain, so this is our low frequency gain, and this is a frequency shaping term. Now looking at this in terms of our control system, we have V out over Vi with respect to S is equal to A naught divided by 1 plus beta A naught times 1 over 1 plus S divided by omega H times 1 plus beta times A naught. So again, frequency shaping. DC gain. This term beta times A naught is called the loop gain. And of course, this is the loop gain at DC, or omega is equal to 0. Alright, this is actually called the closed loop DC gain. We want to use proper terminology here. Alright, so what if A sub 0 is large? Well, if A sub 0 is large, then V out over Vn is approximately, with respect to S, is approximately equal to 1 over beta times 1 over 1 plus S divided by omega H times beta times A sub 0, or A naught. And if we substitute our value for beta in here, we get 1 plus R2 over, or sorry, RF over R times 1 divided by 1 plus S divided by omega H times A naught times R1, sorry, R divided by R plus RF. Alright, this is exactly what we derived using KVL and KCL, only it's a little bit less of a brute force method, and we get to use a little bit of our control theory knowledge. We get the same result, so that's important. We can see that our op amp, indeed, if beta is very large, if beta times A naught is very large, or if A naught is very large, we see that our DC gain is 1 plus RF over R, exactly what we'd expect, and we have some frequency shaping term that has a pole, omega H, that is enhanced by the gain of the op amp and the feedback factor. Alright, in the next part of the lecture we will look at what the implications are if A sub 0 is not large.